Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at the AQA A-Level Chemistry Year 2 section on aldehydes, ketones and the nucleophilic addition reaction. So by the end of this lesson you should be able to do the following things. You should be able to apply IUPAC rules for naming aldehydes and ketones. Be able to draw the nucleophilic addition mechanism for reactions with aldehydes and ketones with both sodium borohydride and either hydrogen cyanide or potassium cyanide, and explain why during the nucleophilic reaction it is possible to form optically active enantiomers, and finally describe and explain the formation of a racemic mixture and explain why they are optically inactive. The first thing to look at then is this thing, the carbonyl group. In this example, we're going to imagine that our carbon is our purple atom in the middle, and that is got a double covalent bond to an oxygen, and we have these two side groups, and we're going to have one of them as an R group, which could be a methyl, ethyl, or any carbon chain, and our other one on the side here can be a number of possible things. The X could be either another R group or another hydrogen in our first examples. If it was another R group, say a carbon chain, then it would be a ketone, and if it was just a hydrogen, then it would be an aldehyde. The second things that these could be, as we'll see later on in the subject, is it could be a Cl, it could be an OH, or it could be an OR group. If it's a chloride, then it would be an acyl chloride. If it was an OH, it would be an ethanoic acid, and if it was an OR, it would be an ester. And indeed we can have one other possibility here. We could have O carbon double bonded to an oxygen and another R group, and in that case it'd be an acid and hydride. Let's come back and just look at the carbonyl group on its own. So our purple one, that is our carbon, we can see if that's a carbon bonded to an oxygen, the oxygen is comparatively speaking electronegative and therefore is going to be delta negative, and our carbon would be delta positive. What that means is, I'll show you again here, that we're going to end up with a carbon which is susceptible to attack by nucleophiles. And we'll have a look at this in due course. A nucleophile being something with a lone pair of electrons and or sometimes a negative charge. The other important thing about our carbonyl group here is if we're looking at it face on, we're looking at this left-hand version. If we turn it to the side, we notice that the molecule is flat, in which case we term that this is planar. Importantly then, our acyl or carbonyl group is the carbon double bonded to the oxygen, and the reactivity of the rest of the molecule will then depend on what we've got attached to the carbon group, which will affect the polarity, that is the number of electrons or amount of electron density to be more precise, on that central carbon. Then we're going to look at aldehydes and ketones in particular, and we're just going to remind ourselves of how we use them in nomenclature and also what they look like. Again, we have the carbon double bonded to the oxygen, and if we have a hydrogen as our X group, then we have ourselves an aldehyde. We name the aldehydes by using the suffix al at the end of the name. If instead of the hydrogen we've got another R group, we have a ketone. Here we've got the carbon still double bonded to the oxygen. We've got an R group, remember, it doesn't have to be the same. And here we get the suffix -one if it's a ketone. If there's more than one functional group, we may well give it the prefix if required, which is oxo. Now the carbonyl group, remember here, the delta positive carbon and the delta negative oxygen mean that we have a polar bond, and the carbonyl group is susceptible to nucleophilic attack, and therefore we're going to go now and have a look at the nucleophilic addition reaction. We're going to look here at the general mechanism for the nucleophilic addition reaction, and that's going to be to aldehydes and ketones, and therefore we're just going to label our group here as X, and we're going to have R as our other carbon chain. Remember, the carbonyl group is polar, which allows for that nucleophilic attack. And the nucleophiles that we're interested in and that we're going to be looking at in this part of the course are the nitrile group and the hydride group. We'll come back to those in a minute. The general mechanism then is, remember, we show electron movement with the curly arrows, and they go from an area of high electron density, our lone pair of electrons, and we get attack on that carbon, which is delta positive. The electrons then from the bond move onto the oxygen atom. This gives rise to a tetrahedral intermediate with the nucleophile now attached. We've got a negative charge on the oxygen and a lone pair of electrons. These reactions are usually done in aqueous conditions, and therefore there's already hydrogen ions present, and the lone pair of electrons from the oxygen can now attach the hydrogen ion. What this leaves us with then is a product which is tetrahedral in shape with a nucleophile added. We'll now look at each of these reactions individually. First of all, we'll look at the nucleophilic addition reaction with sodium borohydride. Importantly, sodium borohydride provides a source here of hydride ions. That is a negative hydrogen where it's gained an electron. We're going to look at this to the addition of ethanal, the aldehyde ethanal. So the lone pair of electrons again attacks the delta positive carbon, and then from the bond we have the electrons going on to the oxygen atom. We now have ourselves a tetrahedral intermediate, and the lone pair of electrons on the oxygen negatively charged atom here are going to donate their electrons to hydrogen ions, and we then end up with our product, which in this case is ethanol. The conditions for this reaction are we use sodium borohydride, and we do these in water with methanol present. Overall, we've added hydrogen, and we can also describe this as a reduction reaction. And we're going from the aldehyde or ketone to the respective alcohol. If we've got an aldehyde going, then we end up with a primary alcohol, and if we have a ketone being reacted, we end up with a secondary alcohol. So the aldehyde goes to a primary, and the ketone we end up with the secondary alcohol. We can write these two reduction reactions as shown. So if we have an aldehyde, we can show our reduction by putting the hydride ion in a square brackets to indicate reduction, a bit like we did for oxidation last year, and we end up with the primary alcohol. And if we're using the ketone, we can use the hydrogen shorthand notation for reduction again. And we end up with the secondary alcohol, as shown there. That's reaction with hydride. We're now going to look at the addition reaction here with a different nucleophile of the nitrile group. And this reaction can be done either with acidified KCN, which is potassium cyanide, or with hydrogen cyanide gas, and is done at 25 degrees Celsius. The nitrile group is then a carbon triple bonded to a nitrogen with a negative charge occurring on the carbon group, and it's going to attack as a nucleophile again to our delta positive carbon and our delta negative oxygen. This time we've got a ketone and we've got the molecule butanone, because we've got 1, 2, 3, 4 molecules. So the reaction with butanone. The lone pair of electrons again on the carbon, attack the carbon, and then from the double bonded electrons to the oxygen go on to the oxygen atom. That then bonds the nitrile carbon to the central carbon, and we have a tetrahedral intermediate again with the lone pair of electrons on the oxygen along with a negative charge. This lone pair of electrons now bond to a proton, and we form the final product. In this product we've got an OH group and a nitrile group, and so these we call hydroxy nitriles. So to name this particular hydroxynitrile, we start numbering from the carbon at this end. 1, 2, 3, 4. This molecule is therefore 2-hydroxy, which deals with the OH group, 2-methyl, which deals with the methyl group, because it's 4 carbons, and because it's an alkane, and then because we've got a nitrile group we add an E, so it's butane nitrile. We add the E because otherwise we'll have 2 consonants together, and we have 2-hydroxy 2-methyl butane nitrile. If we look at this reaction, then we can see the product here is producing something which has got a carbon in the center, and then that carbon has got 4 different groups attached to it. That means we can identify this carbon as a chiral carbon, and this molecule is going to be an enantiomer and will be optically active. We can draw the enantiomers that will be formed by having the carbon in the middle, methyl group coming to one side, the C triple bond N coming out towards. We have the ethyl group going away, and the OH group going up, giving us a enantiomer. We can draw the mirror image of this like so, with the OH going up. Remember, we're going to draw it in the same way, but we're just going to switch these 2 groups around. So instead of the nitrile group, we'll have the ethyl group, and we'll have the CN away from us. And there we have 2 enantiomers, and therefore the molecule should be optically active. However, the products from these reactions tend not to be optically active. Why is that? Well, that's because we form a racemic mixture, which means we have a 50-50 mix of enantiomers. The question here is, why do we end up with a 50-50 mix of enantiomers? Well, to do that, we just need to look at the starting reactant. If you remember earlier on this lesson, we pointed out that our carbonyl group, from which our optically active enantiomers were made, or optically inactive enantiomers were made, is planar. And what that means is there is a chance that the nitrile group will either attack on either side of the plane. We tend to say it will attack above or below the plane. So if the nitrile group attacks from this side, then all the other atoms get shifted this way. Whereas if it attacks from the other side, then the molecules or the atoms get shifted this way. There is equal chance of the nucleophile attacking from either side, and therefore we end up with two products which have got an equal number or 50-50 mix of enantiomers, and therefore, because it's a racemic mixture, it is optically inactive. Okay, so that brings us to the end of the lesson. You should now be able to use the IUPAC rules for naming aldehydes and ketones, be able to draw nucleophilic addition mechanisms for reaction with aldehydes and ketones for sodium borohydride and either hydrogen cyanide gas or potassium cyanide acidified, explain why the nucleophilic reaction is possible and why it can form optically active enantiomers, and describe and explain the formation of a racemic mixture and explain why these are optically inactive. That's the end of the lesson, and I'll see you next time.